Hooke's law. Here we have a spring of length L. If we apply a force to extend the spring by an amount x, and then plot a graph of the force applied against the extension, we get a straight line through the origin. This shows us that force is directly proportional to extension. This is Hooke's law, which we can write like this. Adding a constant of proportionality produces an equation, and the spring constant K is given by the force divided by the extension. The stiffer the spring, the greater the spring constant, and the units of the spring constant are newtons per metre. Here's a simple example. An archer exerts a force of 250 newtons to pull the string of a bow back by 40 centimetres. Calculate the spring constant for the bow. Well, spring constant is force divided by extension, which in this case is 250 newtons, over 0.40 metres. This comes out at 625 newtons per metre. Looking at force against extension again, but now going a little bit further, we see that the trend doesn't continue. If we now remove the load, the spring would contract along this line, showing permanent extension. The spring has been damaged. The point here is called the elastic limit. This is where the spring no longer obeys Hooke's law. Now to look at the energy stored in a spring. Again, we apply a force and extend our spring by an amount x, and again we plot our graph of force against extension. The area underneath the graph will be product of force and distance, which is the work done in stretching the spring. Therefore the energy stored within the spring is represented by this triangle. The area of the triangle is given by half base times height, which in the terminology given is half times the force times the extension, which I've reproduced here. But also from previously we know that the force is given by the spring constant times the extension. So we can substitute this term for the force here to give the energy stored as half the spring constant times the extension squared. Working through the energy from the previous example, we have the archer exerting a force of 250 newtons to pull the string of a bow back 40 centimetres again. Now we have to calculate the energy stored in the bow. Well, energy is half times force times extension, which is half times 250 newtons times 0.40 metres, giving 50 joules. The archer now produces the same extension on a bow with a spring constant of 850 newtons per metre. How much energy is stored here? Well, now we need the other form of the equation. The energy is half times the spring constant times the extension squared. Putting in the values with the spring constant of 850 newtons per metre and the extension again 0.40 metres gives an energy of 68 joules.